Hi, and it's great to be back, even if only in this kind of funny format to the Royal Institution. I'm going to share my screen. So the title of this talk changed a bit only because talking about absolutely everything is a bit much for an hour. And in fact, let me show you a picture just to start with. So, I have this new book out called Shape, and that's the subtitle, The Hidden Geometry of Absolutely Everything. Just to keep straight what this book was about was not so easy. And so what you're looking at is sort of my picture, which appears as the frontispiece of the book, of not even really all, but just some of the things that the book is about and which ones are connected to which other things by relations of circumstance or intellectual affinity or whatever it may be. It's meant to be a kind of map of the book. I call it like a Tolkien map because, that if you sort of like read Lord of the Rings or something, it's kind of complicated where everything is. And you need to know like where do the elves live? Where do the dwarves live? How do you get from the dwarves to the orcs, et cetera, et cetera. It's kind of like that. So I'm just putting this up to sort of apologize for not talking about absolutely everything. In a talk like this, I'm going to sort of follow one strand of the geometry, better to say geometries, that this book is about. But as your eyes gaze over this, if there is other stuff on here that I totally don't touch in this talk and you want to talk about it, just ask me. We have a nice long question period, and I'm happy to talk about anything that's on this page or anything else. And I'll put this slide up again at the end of my talk and leave it up as I ask for questions for those who want to hear it. So let me start tonight's talk with a puzzle, which is just, what is this? What is this list? Kendi, Jean, Abby, Fleury Meyra, Jean, yes, Jean again, but spelled differently, Starlo, Kaming, and Batilia. Okay, I'm gonna let you think on that. It's not supposed to be obvious. But to start to tell a story of what this thing is and answer the puzzle, which I promised to do by the end, we got to go back to 1904. And the person you're looking at here is Ronald Ross. Not such a household name now, but in 1904, one of the most famous doctors in the world. He had just won the Nobel Prize in medicine in 1902. And he won the Nobel Prize because he was the person who discovered that malaria was transmitted by the Anopheles mosquito. Obviously, a discovery of huge import for public health around the world. So this headline you see, and I apologize for it being so blurry, but this is what happens when you do your best to reproduce a very tiny piece of microfiche on a large slide. The headline says, "Mosquito Man Coming." Ronald Ross in 1904, what was he doing? He was on his way to St. Louis in the middle of the United States for the Louisiana Purchase Exposition, which was there to commemorate the 100th anniversary of the Louisiana Purchase that nearly doubled the size of the United States. Now, if you really know your U.S. history, you know that that took place in 1803, so it was actually 101 years later, but it was a big event. It's hard to get these things planned completely on time. More than 20 million people came. It was held at the same time and place as the Olympics, which is also in St. Louis, and the National Convention of the Democratic Party. Helen Keller was there giving a talk. Geronimo was there giving a talk. Some people say the ice cream cone was invented there. It was a very, very big deal for the early United States as it sort of introduced itself onto the world stage. And in September, there was what was called the International Congress of Arts and Sciences, almost at the very end, where the convention invited really the most notable scientists from all over the world to gather in the middle of the United States to talk about their research and what was going on. And Ronald Ross was among them, as were several other people we'll talk about today. Ross was giving a lecture called The Logical Basis of the Sanitary Policy of Mosquito Reduction. So I have to admit that does not sound like that much of a barn burner of a talk, right? And it definitely doesn't sound like that talk would be the beginning of an entire new field of mathematics. But it was, and that's kind of the story I want to tell you about. starting with Ronald Ross in 1904. So what I'm going to show you first is a picture from Ronald Ross's talk. By the way, you know what I was doing while Martin was introducing me? I know I'm supposed to be hanging on every word, but I just, as Martin was saying that the Royal Institution has been active for more than 200 years, or maybe he said almost 200 years, I was like, gosh, like Ronald Ross like probably spoke at the Royal Institution. And I looked it up, and yes, he did on March 2nd, 1900. I found, I quickly Googled and found, so I guess 120 years later, here I am reminding you of what Ross was working on. I think probably none of you were there for that last talk in 1900. So here's the question Ross was interested in this moment. You see, once you know that malaria is spread by mosquitoes, it's kind of natural to know, okay, what do you do if you want to get rid of malaria? You get rid of mosquitoes. But you can't get rid of all mosquitoes. And, you know, then as now, and maybe I'll say a bit in a moment about sort of what Ross has to say about contemporary issues in pandemic control, which of course are relevant. But then as now, epidemic control is not about eradication. It's not about perfectionism. Making an organism extinct is really, really hard, and you probably can't do it. So what does that mean? Does that mean your efforts are doomed? No, definitely not. Whether we're talking about 2021 or whether we're talking about 1904, he said, let's suppose you can clear out the mosquitoes from some region, make some small region of land mosquito-free. Let's say a circle like the one I've drawn here. Well, there's still going to be mosquitoes elsewhere. And those mosquitoes are eventually going to find their way back in to this area that you've cleared. And the question is, and here's where it's kind of a math question, how fast? How much time have you bought yourself if you clear an area of a certain known size of all mosquitoes? So that becomes a question of, well, how fast do mosquitoes go? Okay, maybe you know something about mosquitoes. Maybe you know how far a mosquito can fly in a given day. I don't particularly know the answer to that question, but that's something a mosquito biologist would know. And so what you can see on this picture is, well, maybe a mosquito can fly a mile a day. Let's just posit that. Doesn't matter what the exact number is. So then you might say, like, well, in 5 days, the mosquito can fly 1, 2, 3, 4, 5 miles. So it can get pretty far. But here's the thing. Mosquitoes are not goal-oriented organisms. Not to slight them. That's just how they are. They don't make a plan and stick with it day after day. They're wanderers. Let's say, as a sort of simple model, let's say that each day they wake up and they decide to fly a certain direction. Maybe the first day they fly off this way, and the second day they fly off some other way, and the third day some different way, and the fourth day some different way, and the fifth day some different way. So even though the mosquito is doing a lot of flying, this particular mosquito, choosing its directions at random, does not end up very far from its starting point. And from the point of view of disease control, that's good, right? That means that the mosquito is not going to sort of jet off in some direction and move a very long distance in a week or a month or 2 months. It means that in its kind of random flitting around, it's going to sort of typically not wander very far from where it starts. But the question is how to quantify that, how to estimate how far the mosquito is likely to go, given that it's not going to go given that it's very unlikely to go the maximal distance it could go if it sort of determinedly and doggedly went straight off in one direction. So this was fundamentally a math question. And maybe because we have a little bit of extra time together tonight, what an interesting character Ross is. You know, as I said, one of the most decorated doctors in his time. But he's kind of a bitter guy. He's kind of always unsatisfied, always feels underappreciated. He was constantly like lobbying Parliament to like give him more and more monetary prizes, to like name more things after him. And part of it was that he writes in his memoirs, it's kind of shocking that he never really felt that strongly about medicine. He never really felt like that was the thing to be doing. There was two things that he valued much more. One of them was poetry. He was super into poetry. He actually published a lot of poems and sort of clearly thought of that as a higher calling than medicine. He wrote a lot of poems about how underappreciated he was for his mosquito discovery, by the way. Maybe I should, no, I'm not going to do it. I could read from his poetry, but I won't. The other thing he really liked was mathematics. The other thing he really held in very high esteem, higher esteem than the stuff he actually did for a living, was mathematics. So he rather proudly said of this talk, he said, they invited me to talk about medicine, and I came and gave a talk about mathematics to a group of doctors who were not expecting it and had no idea what I was talking about. So I think it says something about Ross's personality that this was something he said, not embarrassed that he screwed up his talk, but sort of proudly that this was what he brought. And in fact, I'm going to go off my slides here just to say, Ross later develops the ambition to develop what he called a theory of happenings, a mathematical theory that would, like Newtonian physics, basically cover every kind of human activity, especially anything that could spread through a human population, like a disease. And while we're talking books, let me recommend Adam Kucharski is a wonderful book. Is it just called Contagion? I don't have the title quite in my mind, but it's which is where I learned about this this later theory of Ronald Ross. But he did something pretty smart. At this point, he understood he did not have the math on his own to set up such a theory. He brought in a professional mathematician, Hilda Hudson, who was an algebraic geometer, and they together developed the Ross-Hudson model of contagion, which underlies basically every model you've seen of COVID spread in the last year, and I know you guys have all seen a lot. They all descend from this work that Ross and Hudson did in around like 1915, 1916. And that's a story that's told in the book. It's not a story I'm going to tell tonight, but while we're talking about Ross, I just felt I had to mention it. So what does Ross do in this moment? Ross is presented with this problem that he does not know how to solve. How far should we expect this wandering mosquito to go that chooses its direction randomly every day? Once again, he knew he didn't quite have the mathematical chops to solve this problem himself, but he knew who to ask. He asked Karl Pearson. That's who you're seeing on the left-hand side of this slide. He said, Pearson, do you know how to? And so Pearson was probably the most notable statistician of his era in the UK. Also, by the way, like a phenomenal popularizer. He was the Gresham lecturer in geometry and gave a lot of talks, just sort of like this one in London about the geometry of statistics, a subject that he in some sense invented. Pearson said, I don't know either, but I know what to do. I'm going to write a letter to nature. This is what you did in those days, right? You couldn't like post your question on Twitter. If you wanted scientists to read something and think about some problem that you were interested in, you wrote into the letters column of Nature and said, can anybody help me with this? And so what you see is a short letter. This is the letter that Pearson wrote in 1905, The Problem of the Random Walk. And this name is what this subject has been called in mathematics ever since, the theory of random walks, given to it by Pearson. You might notice that there's nothing in here about mosquitoes, and this was on purpose. Pearson told Ross, this is a little bit of mathematical sociology. I'm not going to say this is a problem about biology because the mathematicians won't work on it. So we took out all mention of biology. He also, much to Ross's annoyance, took out all mention of Ronald Ross. You may note he presents it as if it's his own problem. Well, what happens from here? First of all, this particular problem is quickly solved. In fact, it's solved so quickly that it was solved 20 years earlier by Lord Raleigh, who sort of like writes in to say, like, I already did this, Pearson. But that's not really the... What's kind of cool about this is that this idea of the random walk, which I've told you about coming up in the context of disease control and coming out of mathematical biology, is not coming up only there. Somehow, in this time period between 1900 and 1905, this same question is coming up again and again around the world. And it's an example of something that we see in the history of mathematics a lot, that sometimes the world is just ready for some particular idea. And when that happens, it pops up everywhere at once. Let me give some examples. So what's happening in Paris at the same time? In Paris, there's a guy called Louis Bachelier. He's a grad student at the Sorbonne, but he is not a typical student. He doesn't come from the upper classes. He doesn't have the usual lycée education. He was an orphan. He had to work before he went to school. And he worked in the Bourse. He worked in the big bond market in the center of Paris. And what he wanted to study was the fluctuations of bonds and stock prices. He wanted to use the tools of mathematics to study that, much as Ross wanted to use the tools of mathematics to study disease spread. And I can tell you that in the very high-flown world of Parisian mathematics at that time, this was like very, let me use a French word, it was very déclassé. It was not the kind of thing the mathematicians were supposed to think about. It was the mathematicians were supposed to think about, like, if they were even working on applied stuff at all, it was supposed to be like the three-body problem, like celestial mechanics, like things floating around in space, not like people buying and selling stuff, which is a little low. But Bachelier's advisor was Henri Poincaré, the great geometer of early 20th century France, who was a very open-minded guy. And by the way, he was also a speaker at the 1904 St. Louis conference. So a story I won't tell tonight, but we can talk about, which is also told in the book, is that Poincaré, speaking 2 nights after Ross on the same stage, talking about the crisis in physics that was about to be resolved by Einstein in this sort of astonishing geometrical feat 1 year later in 1905. But we're not talking about that. We're talking about Bachelier. And Bachelier said maybe nothing is driving these prices. Maybe it's just chance. Maybe a good way to think about what's happening with the price of a bond is that every day it wakes up and it decides to go up or down, essentially at random. And he asked, is this a good model? Is this actually describe the way we actually see prices in the market work? And of course, to answer that question, you have to know, well, what does happen if a bond chooses which direction to go at random every day and does that? And as you can see, this is essentially the same question that Ross was asking. A little bit easier because in Bachelier's work, it's only going up and down. There's sort of only one possible direction of motion, but the same idea, treating a stock as a random walk. And what Bachelier found is that actually this model does do a pretty good job of reproducing the way we actually see these prices behave. In other words, you can look and look and look for some governing principle that tells you what the stock market is going to do, but quite possibly there is none. Quite possibly it's pure noise, pure randomness. So he writes this famous slogan, and I like the of his thesis, so I screenshotted this for you directly from his thesis, where he writes, "L'espérance mathématique du spéculateur est nulle." Like the mathematical value of speculation is zero. That's the conclusion he comes to, which he calls a fundamental principle. At the same time, and I don't have a slide for this because you guys all know what Einstein looks like, but Einstein is in Switzerland, work on relativity, but this is something else again. A big mystery of physics was what was going on with Brownian motion. Okay, so what's Brownian motion? It's if you have like a little chunk of something, some small particle suspended in a liquid, and you look at it in the microscope, what do you see? You see this particle kind of jittering around. It's moved as if alive. This was discovered by the botanist Robert Brown hundreds of years earlier. I didn't put the year in my notes. He had first discovered it with a piece of pollen. So his first thought was like, wow, this is crazy. This piece of pollen, it still maintains like some kind of vitality even after it's been separated from the plant. But being a good scientist, he tried it with a bunch of other organic things, but then he tried it with a lot of non-living things too. He tried it with like shavings from his window pane. He tried it with like various pieces of minerals lying around. Actually, my favorite of all, he like lists the things that he tried, putting it in a little drop of liquid and looking at it in his microscope. And one of the things was a fragment of the Sphinx. Like that was just a normal thing that you'd have in your lab. I don't know why. He doesn't explain why he had a fragment of the Sphinx or how he happened to come by it, but like everything else he put in his drop of water, it jittered and moved as if alive when he looked at it under his microscope. So we quickly realized this has nothing to do with biology, has nothing to do with some kind of life principle. Just things do that, and nobody knew why. But there was a popular theory, most associated with the physicist Ludwig Boltzmann, who was also in St. Louis, by the way. He and Ross had dinner together. Boltzmann was one of the most fervent advocates of the idea that matter was made of tiny little molecules that we couldn't see. This was controversial at the time. But if you believe that, that gives a possible explanation for why Brownian motion happens. Because if in the drop of water, there's a particle, which we can see in the microscope, and millions of water molecules, which are much smaller, which we can't see in the microscope, but are moving around at high speed and constantly knocking into the particle, pushing it one way or another, that might explain the mystery motion. But in order to test that, you have to say, well, so the model would be that molecules are constantly, millions of times a second, running into this particle and pushing it, and essentially coming at it from a random direction and pushing the particle in a random direction at some speed. And in order to test whether that's a good, that would produce the behavior we actually see, we have to say, like, well, what would a particle look like if it were millions of times a second picking a random direction and moving a little bit that way? Guess what? Same problem, right? Exact same problem. And Einstein solved it too and saw that, oh yeah, indeed, that exactly tracks every measurement we can make of the way that particles actually behave. So this, at the time, was the most definitive blow yet in favor of the molecular theory. Okay, so I've told you about what was happening in mathematical biology, and I've told you about what was happening in mathematical finance, although the financial people didn't actually really catch on to what Bachelier was doing for like 50 more years after that, but that's okay. And I told you about what was happening in physics, but I didn't actually tell you about, to me, the craziest place that this came up. And so let me do that now, because we got to get to the puzzle. So this is Andrei Markov. And what I want to tell you about is, surprisingly, an argument about theology. Where is this going to come from? Okay, let me tell you the story. There's a famous theorem called the law of large numbers. It's due to Jacob Bernoulli. I'm not going to state the theorem formally. It's not that kind of talk where we state theorems, but here's basically what it says. And it's a fact that you guys are probably all familiar with. That if you flip a coin a lot of times, the proportion of heads is very likely to converge towards 50%, right? I mean, if you flip 10 coins and 6 of them come up heads, 60%, that is not surprising. If you flip 100 coins and 60 of them come out heads, that's pretty surprising. If you flip 1,000 coins and 600 of them come out heads, that's really surprising. The more coins you flip, the more strongly you feel, the more likely it is that that proportion is going to be within some very narrow bound, around 50%. Actually, Carl Pearson, whose picture we saw a minute ago, used to like to illustrate this by like literally flinging open a bag of 10,000 pennies like on the floor of the classroom and making the students count the heads. I still haven't decided whether I think this is like great pedagogy or awful pedagogy, but it was definitely something he was like well known for doing as a statistics teacher. Okay. Once people knew this, they started to see over the years, especially as quantitative social science got started, that statistics of human behavior tended to settle down to averages in just the same way that coin flips did. If you look at proportions of male to female births, or date of first marriage, or number of children, or whatever, I mean, these things might vary some with time, but in any given short time span, you look at what people do and they seem to converge to averages, to some kind of general social average of how many children each couple has, or how many crimes are committed per 100,000 people, or such and such and such. And why this was a topic of hot controversy in the scientific world. And it also created a lot of anxiety, because people felt, does this mean that we're just like coins? We're just automata that are sort of like operating under the same sort of meaningless laws of randomness as coin flips do. And that was the way a lot of people thought about what these statistical regularities of human behavior meant. But as you can imagine, a lot of people didn't like that idea. And one of the people who didn't like it was Markov's enemy, Pavel Alexeyevich Nekrasov. They led two rival schools of Russian mathematics. Nekrasov was in Moscow, Markov was in St. Petersburg, but it was more than just city rivalry. Nekrasov was an ultra-conservative, ultra-devout Russian Orthodox theologian. He was, in every respect, a man of the Tsarist establishment. So we're pre-revolutionary, right? We're still in this 1900 to 1905 period. Markov, on the other hand, is a fervent atheist, an enemy of the Orthodox Church. He actually, after Tolstoy was excommunicated, he was very jealous, and he wrote to the church to demand that he also be excommunicated. He's like, I'm just as much of a heretic as Tolstoy. You should excommunicate me too, which they did. He was pleased about that. He was actually widely known as Neshtovy Andrei, like a furious Andrei, because of like all the sort of angry open letters he would write to the newspaper. So these guys start out enemies just kind of ideologically, and then it gets worse. Why? Because Nekrasov is one of those who cannot accept that human beings are just random automata. If the theorem seems to say that, he said the theorem must be wrong, but the theorem's not wrong. So what do you do? He thought about this a little more, and then he made the following claim. He said, but here, a key input to the law of large numbers is the independence of the coins. The different coin flips are independent from each other. If that's not true, the theorem might not work. Like if the coins are constrained to always fall the same, then it won't settle down to 50%. It'll be either 100% heads or 100% tails. So Nekrasov said, aha, you thought that Bernoulli's theorem meant that humans were mindless automatons like coins. But what it actually means is that we're independent from each other, that we have free will. Well, Markov was not having it. I think from Markov's point of view, okay, it's okay that we have these different religious views. What's not okay is for Nekrasov to say it's mathematics. Now in Markov's view, now something really important is involved, the honor of mathematics. And so they have this big fight, and what Markov does is he draws the following kind of picture. So I'm going to write this sort of in terms of mosquitoes, because that's what we're talking about. Markov says, consider the following scenario. You have a mosquito, and let's suppose for simplicity, it only has two places it can live, two bogs. I guess that's where mosquitoes live, bog 0 and bog 1. And on any given day, the mosquito makes a random choice. Maybe the mosquito is pretty comfortable in both bogs. So if it's in bog 0, 90% chance it's going to stay in bog 0. And maybe 10% chance it'll jump over to bog 1. If it's in bog 1, maybe bog 1 it likes a little bit less. There's actually a 20% chance it'll jump over to bog 0. But still, most of the time, it'll stay in bog 1. And what Markov showed is that if you let this mosquito live a long time, it too will settle down in a very statistically regular fashion to spend about 2/3 of its life in bog 0 and 1/3 of its life in bog 1. Just like a sequence of coins will converge to be 50% heads, 50% tails. Even though certainly where the mosquito is one day is not at all independent from where the mosquito is likely to be the next day. In fact, they're very highly correlated. It's very likely to be in the same place day to day. So what Markov was explaining to Nekrasov is like, yes, if you have independence, you get Bernoulli's theorem, you get this kind of statistical regularity, but that doesn't mean that if you see the statistical regularity, it must have been because of independence. There's lots of non-independent things that give you this regularity too. So he was refuting Nekrasov's claim that he had somehow proved the existence of free will by mathematics. And I got to say, I'm just, speaking for myself, I think there's like a very long multi-century history of people trying to prove philosophical claims about the nature of humanity, the nature of existence, the nature of the deity by mathematical means. I'm kind of a skeptic of all such attempts. I think math is wonderful and does a lot of incredible things, some of which we're going to talk about tonight, but it doesn't do that. That's not what it's for. And that's certainly what Markov thought. And at least on the mathematical point at issue in this argument, he was clearly the winner. And even today, another name for a random walk, or at least a certain kind of random walk, is a Markov chain. Because Markov was the person who, I told you about a lot of examples that individual people came up with. Markov was the one who really sort of made this into a theory and understood like the theory of all kinds of processes of this type. What's funny is that So I'm going to take this in kind of a weird direction because Markov was actually not interested in mathematical biology at all. He was tended to turn up his nose at actual applications, but there was one that he was willing to talk about because there was one thing that both atheist and religious Russians definitely valued and really wanted to think about a lot, and that is the poetry of Alexander Pushkin. And that was where Markov took this a few years later. He took Pushkin's famous first poem, Eugene Onegin, and wrote it as a sequence of consonants and vowels. He wrote out like 10,000 letters of this book, just marking whether they were a consonant or a vowel, and then said, okay, if one letter is a consonant, what's the next letter likely to be? And he found that it was pretty likely to be a vowel. Like 2 consonants in a row is pretty rare. About 2/3 of the time, to be precise, 66.3% of the next letter after a consonant was a vowel, whereas then 33.7% of the time it was another consonant. Whereas if you were a vowel, double vowels were even rarer. Only 12.8% of the time would a vowel be followed by a vowel. And so this picture, you see this is formally very much like the mosquito moving between 2 bogs. He was modeling Pushkin as a kind of poetical mosquito kind of moving back and forth between consonant and vowel. And I think you'll agree, this is like a pretty impoverished and limited way of thinking about poetry. It throws out a lot of what's special about Pushkin, of course. But what's cool is that he was able to show that you actually get different Markov chains from different writers. He sort of did the same thing with a novel by another Russian writer, now, at least to my knowledge, kind of forgotten, Aksakov, and found that you just got different values from these numbers. The patterns of consonants and vowels were different. So Markov chains now, and there's so much of the story I could tell, and I'm only going to tell a little bit of it tonight, are fundamental to, I mean, still to mathematical physics, certainly to computer science, to like all to the process of legislative districting, which I write about a lot in the book, and I won't touch tonight because it's a sort of US-centric political question. Maybe I'll give, okay, I got to give one example of like, of how this is used. So how does Google work? I think I can tell you in one picture. I'm going to try. This is intentionally left blank, by the way, because I'm about to write on it. I don't know how old everybody is in the room, but if you're about my age, that's about the boundary for can you remember the difference between the internet before Google and the internet after Google? And if you are younger than me and don't know that, let me tell you, it was really different. It was an instant, humongous change in your ability to search. And why is that? Because Google developed something called PageRank, which enabled it to say, you know, I searched for some word like frog, and a lot of pages come up that have the word frog in them. And Google was able to make a very good assessment of which ones were the most important using the structure of the web itself. How do you do that? I'll write PageRank so we can all see what it is we're talking about, if I can spell it. So a natural thing you might think is, I guess a page is important if it has a lot of links to it. That's reasonable, right? It has sort of important web page that you may want to see. Probably a lot of people would link to it. So one thing you could do is say, I'm going to rank the pages by the number of incoming links. And that does not work. And I'll explain to you why it doesn't work. Because if that were the mechanism that a search engine used, here's what I would do. I would sort of have like my frog fan page that I made. And then I would also have, let's say I have Frog Fan 2. I make 2 web pages. And then I make like a lot of links from each one to the other. And I can only draw like 5 or 6, but let's pretend I drew like 10 billion links each way. So then by your proposed mechanism of rating importance, my page would be incredibly important. It would come up at the top of the search race. And then, of course, what there would be some sort of a ridiculous arms race where people were just like putting more and more and more links on their page. Okay, this is not what you want to do. You want something more important like, I don't know, American Frog Society. Is there one? It's probably like the Herpetological Society or something, but we're just making stuff up. So let's say this. This would likely have links. Also a lot of links, probably not 10 billion of them. But more importantly, those links wouldn't just be from my own pages. They would be from other important pages. So, maybe there would be a link from the Royal Institute. You guys probably have talks about frogs sometimes, right? So there might be like a link to sort of some official document of the American Frog Society, or the British Frog Society, or whatever it may be. There might even be links from, the Times or other news organs or stuff like that. And say what's important is not how many links it has. We should say a site is important if it has links from other important sites. But wait, now there's a problem because that's completely circular, right? If we don't know how to define important, how do we know whether the links it has are from important sites? And the answer, as Larry Page and Sergey Brin figured out and then just became like ungodly rich as a result, is to use the Markov chain. So just like, here I'll pop back a little bit. Just like the mosquito flitting back and forth between bog 0 and bog 1, bog 0 is somehow like a little bit better, right? And it ends up spending more time in bog 0. You can imagine something like the mosquito that just is like a little robot that surfs the internet all day long, choosing a random link from every page and wandering the net in this way. And the theory of Markov chains guarantees that this will settle down to something statistically regular, and there is a proportion of its life that the robot will spend at each place. And you know what? That robot is very rarely going to be over here, because how would it get there? If it didn't start there, it would only happen to end up there if somebody else linked to my dumb frog fan pages, which why would they? Whereas it probably would. Many, many paths would take it to the Royal Institution or would take it to the Times, which would in turn take it to the American Frog Society. So it would probably end up here more. So this process of the Markov chain actually does an incredibly good job of sort of showing you which points in a network are important. The ones that are sort of random walker through that network would find itself at more. And it's an idea that in some sense uses, I would say it uses about like college sophomore level math, and it absolutely transformed the web and created this corporate behemoth that we have today. So, but I'm not going to talk too much about the internet. That's all I'm going to say about it. I actually want to sort of follow this idea of studying language. This idea that sort of Markov kind of fancifully did when he was thinking about the poetry of Pushkin, okay? So, because why on earth, you may ask, would Markov reduce this beautiful poem to a sequence of consonants and vowels? Well, it was because like that's what he could do, right? He didn't have a computer. He had to limit the story to just two things, a consonant or a vowel. Well, nowadays we don't have to do that anymore, right? We could keep track of all the letters. Okay, I don't know how many letters there are in Russian. In English, there's 26. So we could track, if we were doing this with English text, we could keep track of all 26 letters. We could even do more. This is another one I'm going to draw for you. So we could also talk about bigrams. And a bigram is just a fancy term for a two-letter sequence, like AA, AB, AC, AD, BA, BB, BC. I guess we could go all the way down to ZZ, this big square of, I guess it would be 26 by 26. So there would be 26 squared. Who's computing this in their head? 676 bigrams in all. And every piece of English text, just as Eugene Onegin can be thought of as a sequence of consonants and vowels, every English text can be thought of as a sequence of bigrams in the following way. If let's say I was doing Royal Institution, then I guess the first bigram would be RO, and the second bigram would be OY, and the third one would be YA, and then AL, and then, maybe we should actually count a space as one of our characters, so you get L space, and so on and so on and so on. And so you can do the same kind of analysis, take an English text and say, if you're at one bigram, what is the next bigram likely to be? So for instance, if I'm at AA, that's pretty rare in English, right? That's not going to happen very much. But if you were there, where might you be? Maybe you'd be talking about somebody whose name was Aaron, and then you would go from AA to AR. That would also work if you were talking about an aardvark or an aardwort or an aardwolf. Okay, I'm having a little trouble thinking of other good words with an AA bigram in them, but that would be something that could happen. But you can imagine other things happening too, but probably with a lower probability. If you were at AB, but if you're at AA, the next bigram has to start with A. If you're at AB, the next bigram has to start with B. And again, ABBA would probably be more common than ABBC because that would mean a word that had ABC in succession. I can't think of one off the top of my head. That probably does exist, but it's not so easy to... Crab cake. Okay, I knew I would have one in mind. So if you were talking about a crab cake, you could get this, but it would probably be pretty rare. So every one of these arrows, just like the arrows in our diagram before, would have some little probability attached to it. And you could think of some body of English text as being described by what probability, the so-called transition probabilities there are from one bigram to the next. Now, okay, ready? We're going forward to the 1940s and Claude Shannon. And what Shannon realized is that this is something that you could use not just to analyze an existing text, the way that Markov had done with Eugene Onegin, but to create text. Once you have these probabilities, you could just say, start with a bigram like AB, and then, like the random walker walking the internet, pick another bigram at random according to whatever the probabilities are that you've computed from your body of English text. So maybe you would find BA was next. So you'd be at BA. And then from BA, you're going to go to, there's lots of places you could go, right? Anything starting with A, BAD, BAE. So maybe the next one is, if you had AB going to BA, going to AT, and your random walk, then you would be like ABAT, ... And by this process, you can produce artificial text. By the way, when Shannon actually did this, it's kind of fun. You can even do this yourself. Computers and computer times are still pretty limited at this time. So he did a version of this where he would just say, okay, I'm going to pick a bigram like AB, and then I'm going to pick a book off my shelf and flip through it until I see an A followed by a B, and then I'm going to see what the next letter is in that word. Maybe he was looking at a book about an abacus, and the next one was A, and so we'd write, great, ABA. Now I'm at BA. Now I pick up another random book off my shelf, flip through it until I find the letters BA in succession. What's the next letter after that? Maybe it's T. Okay, then my next bigram is AT. So sort of using his library as a sort of way of generating random numbers to let him walk through this Markov chain and using this to generate random text. And here's an example of what he got. In nois latwe cratect fror beers grossid pondenome of demonsters of the reptigen is rego actiona of Cree. I love looking at this, man. This is from his famous paper, A Theory of Information in 1948. And I love the way it is clearly capturing something about the English language and the way it works without actually being English, right? This is definitely not English. And yet, it's capturing something of the way we put words together. Nowadays, of course, we don't have to walk around a library the way that Shannon did in order to carry out a process like this. We can use a computer, right? We can use a computer with like tons and tons and tons of English text already stored. And depending on the properties of English text that you start with, you get different results. So I think I'm ready to talk about the puzzle. By the way, again, with modern computation, I wrote down bigrams, of which there were 676. You can use longer letter chains too, like trigrams, which are 3 letters, or even pentagrams, which are 5 letters. There's a lot more of those. I can't write them all on a slide, but a computer is perfectly capable of thinking of an English text as a sequence of 5-letter strings and producing artificial English text thereby. And now I'm going to show you what happens if you do that with a data set I love to play with, the data set of baby names. And ideally, guys, I would have a British version of this, but I don't know if the British government makes this data public. I have not been able to find it. But in the United States, you can get a list of every name that was given to 5 or more babies in the United States. And every year since 1913, you can even have it like broken down by state. It's a great, great, great data set that the Social Security Administration puts out that I've actually used in papers sort of for various data analysis things. But what you were looking at here is if I take the list of every name given to a baby in 1971, which happens to be the year of my birth, that's why I like it. And then you do this bigram thing I told you. You do this Markov chain and randomly walk along it and make artificial baby names. Here's what you get. Teandola, Amberilon, Marahadria, Cassaniane, Quill, and Abenelit. And you can do this with 3-letter sequences. And then you get the thing that we started with, the puzzle. The answer to the puzzle is those are artificial 1971 US baby names produced by a random walk on trigrams where, you pick one at random, KEN, and then you go around in your database and you look until you see something that has a KEN in it. And apparently in that database, the next thing was a D. So the next trigram would be END. I'm trying to think if I can guess what name has a KEND. I can't quite think of it. Once you start to get, the longer the sequence is, the more powerfully you're capturing the properties of the data set that you trained on, the original text, but so much so that you actually just start repeating actual things you found in the data set. So when you start using 5-letter sequences, you actually see it picking out actual names that were used, like Adam and Susan and Kelsey. Again, what's so cool about this to me, so trigrams for me for baby names are kind of the sweet spot where you get really realistic looking names that are not just copies of actually existing names. And what's cool to me is that you can do the same thing with baby names given in 2017 and 1917. And I think you'll agree that in each case, a lot of those are like pretty realistic names. And they somehow, from this very mindless random process, capture something of what you might call the style of naming practices in 2017 and a century earlier in 1917. Those seem more old-fashioned. We're talking about geometry, so let me say a little something about geometry, which you see here. Okay, this sort of seems like, who said this? Seems reasonable. The most common geometric object is the square. A square is a perfect rectangle that has 4 sides. Okay. So nobody said this. This is text produced by a sort of the moment neural net called GPT-3, which in some sense is the modern heir to what Shannon was doing. It's a machine that produces artificial text, but it's really no different in principle from what I just showed you, this kind of Claude Shannon walking through his library, flipping through the books to find the right bigram. Of course, the units for something like GPT-3 are much longer. It's trying to predict the next word or the sequence of words, not just the next letter. But it's working in fundamentally the same way. There's some underlying Markov chain that it's learned through some kind of neural net optimization process, whatever that means. And it is using that to, given some sequence of text, try to predict what's the next word, put that word down. Having done that, now it has a longer sequence, try to guess the next word from there. And it is pretty cool and it is pretty good. And if you train it on your own writing, which is what I did here, it's a little bit spooky because it does capture something of the style of your own writing, which is pretty weird to read. At the same time, just like the sort of artificial words that Shannon made are not real words, the artificial text that the GPT-3 produces is not real text, even as it kind of eerily captures some of the features of real text. So one thing, when I generated this, I was really struck by it, because especially this last sentence, look at that. But squares aren't just shapes. They're also numbers. Boy, as a number theorist like me, I love that because, of course, I'm like, wow, like it really sort of is picking out some actual fact that a square might mean like a shape like this, but also I would say a square, a perfect square is a kind of number like 4 or 9 or 25, a number that is a smaller number multiplied by itself. Like 5 times 5 is 25, it's a perfect square. 7 times 7 is 49, a perfect square. I was like, wow, that's cool. But let me show you what happens when you continue this trial a little bit. It starts to say stuff which syntactically makes sense, and it looks like English, and it even looks like something stylistically, I suppose, that I might write, but it makes no sense at all, right? When we say a square is a number, it's not the number you get by adding the lengths of the 4 sides, because that would be called the perimeter, and then it kind of doubles down, and it's like, that's right, 1 plus 4 equals 2, and 2 plus 4 equals 5, and so on. So it's sort of somehow correctly understanding the kind of thing that it should say without actually having any grasp. I know I'm anthropomorphizing rather badly, but of what it is, so to speak, supposed to mean. And this is super fun to play with, and I highly recommend sort of like looking at instances of this thing, because it really, to me, gives you a very good picture of kind of where artificial intelligence, so-called, is now. It can do amazing things that are also like incredibly limited in ways that I think is really, it's a little bit hard to grasp unless you sort of play with it a bit yourself. So maybe I'll close, because we're just almost at the end of this part of our time together. In the book, I do talk quite a bit about artificial intelligence and machine learning and what's going on under the hood, because the geometry of that is actually not as complicated as you might think. And I think it's very useful to demystify what's going on with a lot of these like truly exciting new developments. And what I want to say, so this is like a sort of cartoon. I think what a lot of people are concerned about is, well, if computers are better than us at, I don't know, playing chess, or carrying out algebraic computations, or translating from one language to another, maybe that's because they're just better than us. So maybe they'll just supplant us in every way. So to use yet another geometric metaphor, which my book is full of, that is a one-dimensional model of difficulty, which I've depicted here, as if difficulty is kind of proceeds along one dimension from easiest to hardest, and the computers are either ahead of us or behind us. So I think that's pretty badly wrong. I think when you sort of think about what kind of problems machines right now can be trained to solve, something I write a lot about in the book in the context of games, especially checkers, or I guess in this context, I would say drafts. It's not one-dimensional. There are many dimensions of difficulty, and I think one of the most interesting parts of the new mathematics of machine learning, yet another new field of mathematics we're developing under our feet, is to understand which kinds of problems machines are good at and which kinds of problems we're good at. Machines are great at playing chess, way better than us, all of us. But a robot can't fold a shirt. And I don't think we really know why that's true. I don't think we really understand yet what you might call the geometric space of problems, how many dimensions it has, what those dimensions look like, and where the zone of human superiority is and where the zone of machine superiority is. So with that, I'm going to put this slide up again. We talked about some of these things, and I hope that questions have been piling up in the chat. I'm just going to sort of circle. Let's see. I always like to see like how far I got and what I talked about. So we talked about Google. We talked about Carl Pearson. We talked about Hilda Hudson and Ronald Ross. And you guys should just start asking questions. And I think Martin is going to feed them to me. The St. Louis Exposition, which featured Ross and Poincaré. Oh, we did a lot today. Bachelier, his students. So Poincaré and Ross are both at the St. Louis Exposition. Boltzmann and the molecular theory. I'm just circling stuff, Martin. So whenever you want to start throwing me questions.
Well, thank you so much, John. That's been an absolutely fascinating tour of